Well, let's go ahead and get started with today's seminar. And so today we're going to be talking about meta-analysis and some of the issues related to both doing and interpreting meta-analyses. So I want to, first of all, talk about meta-analysis itself and what that's about. But most of the time I want to spend on looking at some actual examples of meta-analysis. And the first two I want to look at are those that have some issues with them. The first one related to the particular study population and patients that were included or excluded from the meta-analysis. And then the second study, I want to look at how outcome differences, even though it's might be a similar thing. In this case, it's mortality, but there are some differences in particularly the timing of mortality that may be causing some problems with interpretation. And then I want to finish up with a study where we can look at how we can analyze or get a indication of between study variance, and then end up summarizing our talk. So as I'm sure everyone probably knows, meta-analysis combines published results of several studies, and this is primarily done to either overcome sample size issues if some of the studies are quite small, and then also to estimate what the true effect size of some treatment or therapy might be. The key here is that we have summary data. We don't have actual individual patient data. Another type of meta-analysis that's done is actually using patient-level data. And so you might have the situation where you have several studies, but you obtain the data, the actual patient data from each study, and combine those studies to do a meta-analysis. That's not easy to do because there are often legal issues about getting data from other institutions. So the methods I'm going to talk about are related to summary data. If you have actual patient level data, then that's pretty much similar to traditional statistical analyses. So the first step in doing a meta-analysis is data abstraction, and this is really the most difficult, the most important part of the analysis. And so what we're talking about is a systematic review of every article that deals with the topic of interest. Now, obviously, you're probably not going to get every single article, but that's the goal. And so you have to provide someone who knows how to get these articles, which is, you're like in an academic situation to be a librarian. And then you need at least 2 independent abstractors. In other words, when you get the articles, then you're going to need at least 2 people to go through them independently and come up with the final studies that you want to include in your analysis. When we talk about meta-analysis, we need to understand what the difference is between what are called fixed effects and random effects. And fixed effects are effects that are attributable to a finite set of levels primarily like treatment or therapy. Random effects are effects that are attributable to a large set of levels of a factor, of which only a random sample appear in the data. So for example, if you have just a study that you're doing, clinical trial sites or geographic regions might be an example of random effects, because you're only going to be, limited to the number of sites or institutions that can participate in your study. The patients that you get are always considered a random effect. And I want to talk about why this is important in meta-analysis. And the reason is that if you have data from a given cluster or several clusters, the data might be correlated. And this can affect the computation, particularly of the standard errors, and generally random effects results in larger standard errors, and what that will mean is you have larger confidence intervals. In meta-analysis, published studies, or the study that you get, are considered generally a random effect. Once in a while, I've seen studies that just look at the studies as a fixed effect, but that's not usually done because you can't consider that each study is not just a sample of the studies that may or may not be published. So generally, every meta-analysis that you see published will look at the studies as a random effect. So let me give you an example of that. This goes back several years, the COURAGE trial, where there were nearly 2,300 coronary artery disease patients enrolled in the studies, and they came from 16 Canadian hospitals, 15 VA hospitals, and 19 US non-VA hospitals. And so this is a schematic of what we mean by random and fixed effects. So obviously the fixed effect is going to be the treatment. And so in the COURAGE trial, the analysis was looking at PCI, percutaneous coronary intervention, versus optimal medical therapy. And so that's our fixed effects. The random effects in this study would be the patients, as patients are always random effects. Sites are a random effect, and then the healthcare systems are random effects. So in this study, in the initial study, this would have been the setup and the consideration for comparing PCI with OMT. So there are a number of validity issues related to meta-analysis. One primarily being heterogeneity. In other words, variability in the results between studies. And then we've talked about random or fixed effects, that in doing a meta-analysis, you should always consider the studies as random effects. But in the studies that you have included in your meta-analysis, is there a study or maybe a couple studies that are really influential, that are, say, different from the other studies, and that they are affecting the results? Order, and what I mean by that is the accumulation of evidence, that is the number of years, the span of years that you have obtained the studies for your meta-analysis. And I have an example of that where we have a span of 20-some years. And then, of course, there's always study bias. That is, it may be that the individual studies one of the studies might be biased in and of itself. In other words, you might include a study that's flawed in and of itself. So I'm going to make a few points about heterogeneity. What we would like to see is that whatever differences there are in the results of each individual studies is just due to random sampling variability. And the size or direction of the differences contribute to heterogeneity, but then we have to decide how heterogeneous do they need to be before it becomes an issue. And so meta-analysis issues that might influence the results or bias the results is, first of all, what we call selection bias. That is, you selected studies that either don't include all the outcomes or of interest, publication bias, what's published, what's not published. When we talked about heterogeneity, whether that's can be viewed as random itself, or is it due to something about the studies themselves. And then the data, as I mentioned, you might have a study that is flawed in and of itself. And then artifacts of measurement. This is particularly true of meta-analyses that look at patient-reported outcomes, because usually those are like standard instruments, and those have measurement error associated with them, which is often not taken into account. So the statistical methods are pretty straightforward, because most studies compare two different groups. And so if you have a dichotomous outcome, like mortality, dead or alive, then we're going to do logistic regression. If we have a continuous outcome, then we're going to look at differences in means or rates, which is most of the time going to be just a t-test. And a method that goes back quite a few years, the Simeon and Laird random effects method, is typically what is used for pooling the statistics from each study. And then a statistic that is calculated, the I-squared statistic, is an assessment of the variation in the odds ratios or the mean difference that's attributable to study heterogeneity. And so the I-squared statistic becomes an important statistic to not only present, but to look at in evaluating the meta-analysis itself. So the I-squared statistic ranges from 0 to 100, with larger value indicating greater heterogeneity. And so the question will be what's considered heterogeneous versus not heterogeneous. So other methods that you'll see, which have a couple of those in the examples, is a funnel plot that is typically associated with publication bias, although I think that it can probably identify bias in general. But anyway, I'll show you an example of those. Analysis that is hasn't been done very frequently, but I think is being done more and more as a sensitivity analysis is the jackknife, leave out one. So what you do is you do your analysis with all the studies in there, then you leave out one study and redo the analysis. You put that study back and take out a different one and redo the analysis, and so on, and see if there's any particular study or groups of studies that really influence the results. And then meta-regression is typically used if we want to look at other covariates other than the therapy or the treatment itself that might be affecting the outcome. So this would be analogous to doing multiple regression in a single study. The problem here with meta-regression is that the studies may not have all the same covariates, so you may not be able to, or you may be limited in the meta-regression that you can do. So I want to look at the COURAGE study as an example of studies that excluded or included patients from different populations. And so the COURAGE study goes back on probably 20 years now, but at that time, there was controversy regarding the impact of PCI versus medical therapy on long-term survival in coronary artery disease patients. And the COURAGE trial found no evidence that PCI as an initial management strategy reduced the risk of death or MI alone when added to optimal medical therapy. So obviously this caused some controversy in the cardiovascular world. And so there was after the COURAGE study was published, there was a meta-analysis of 16 randomized trials and then one abstract of comparing PCI versus medical therapy. The problem was, and that recognized by a number of cardiologists right off the bat, is that the selected studies mixed populations. They were a mix of chronic CAD and post-MI or acute coronary syndrome patients. And not only that, there was a major trial available at the time, the occluded artery trial, that was not included in the meta-analysis. So what we did was to reanalyze the data, distinguishing between trials of different patient types, and then we also did an analysis where we included out in the analysis. And so this is the published forest plot of the publications in the original meta-analysis article. And so in terms of what the forest plot is, as you can see, the diamonds are the actual, in this case, odds ratio. The horizontal lines are the confidence intervals, typically a 95% confidence interval. And then usually is drawn in when you're looking at odds ratios, you draw a vertical line there at 1, which indicates no difference. And so you can see that some of these studies are quite small. The one, of course, that is in far superior to the other studies, at least in terms of numbers, is the COURAGE study, where we had over 2,000 patients. And so in this case, they presented both random effects and fixed effects results. So you can see that the point estimate at 0.8 is the same as what is different than between random effects and fixed effects is the confidence interval. So with a random effects model, you typically get a wider confidence interval, which can sometimes lead to different conclusions. And so in this case, because the odds ratio does not include 1, they conclude then that PCI is the better treatment. And you can see then also that what's included usually in a forest plot is the I-squared statistic. And so in this case, at 17%, you can get a p-value for the I-squared statistic. However, I would say that ignore the p-value. The p-value is based on the number of studies appearing in the meta-analysis. So it's actually more important to look at the size of the I-squared statistic itself. So this was their conclusion. But what I have highlighted in their forest plot here are studies with different populations. And so what we did, oh, and then I also, here we have one study that had no outcomes in it. So in that case, even though they're included in there, they're because they have no events, they don't get included in the calculations. So basically, what we did, as I mentioned, we distinguished between the two patient types, CAD or post-MI patients. And then I did a random effects meta-regression of the studies where we included patient type as one of the covariates or as a covariate. And then, of course, calculated the I-squared statistic to assess heterogeneity. And so there was a significant treatment, PCI versus medical therapy by patient type interaction. And so the estimates of the odds ratios for chronic CAD patients was 0.9, which was not statistically significant. However, for the post-MI patients, the odds ratio was 0.5, which was statistically significant, as the confidence interval does not include 1. So we get different conclusions based on the type of patient. And so this is the forest plot redone with the two groups of patients, the CAD patients and the post-MI patients. And so you can see that in the case of the CAD patients, there's no, statistically speaking, benefit of PCI, whereas if we take just the post-MI studies, then there is. Note a couple things here that the I-squared with the CAD studies is 0. So that means that whatever differences there is just due to random sampling variability. For the post-MI studies, the I-squared is 21%. So again, that's not statistically significant, but you have to decide, okay, is 20% an I-squared at 20%, is that meaningful or not? So then, in addition to this, what we did was to include the OAT trial, the occluded artery trial. And I just have some slides here with the background on it. It has the same comparison of PCI with medical therapy, but in post-MI patients. And the conclusion that they came up with is that it did not support the use of PCI for persistent total occlusion or in post-MI patients. And it was a study that was comparable to the COURAGE study as far as size. They had like 2,100, I believe 2,100 patients in it. So this is now the forest plot redone again with the two groups of patients, except now we've added the OAT trial. And so you can see that this now changes things quite a bit. If we include the OAT trial, then there's no longer a benefit of PCI. You can see that the odds ratio is 0.63 and 1 is included in the confidence intervals, so that would not be statistically significant. And then also you note that by adding the OAT study in, that the I-squared goes way up to over 45%, 47%. So adding this trial in makes even more of a difference in the conclusions that we would make based on these studies. So what we can conclude is we have no evidence of a PCI benefit for chronic CAD patients. If we don't include the OAT trial, then there's some indication that it's a benefit for post-MI patients. However, if we include the OAT trial, then the benefit, the PCI benefit, disappears. Okay, so that's illustrating mixing different patient populations and how that might affect the conclusions that you make from the meta-analysis. And so this just summarizes what we found with the CAD trials. We can just assume that differences are due to random sampling variability. For the post-MI trials, there's quite a bit more variability that's reflected by the I-squared, and I'll talk about that later on. And so what we concluded then was that the meta-analysis was not really had valid or had validity problems because it inappropriately pooled different patient populations. Okay, so another study that I want to look at looked at mortality in teaching versus non-teaching hospitals. And so this was quite an extensive study. There were like 30-some thousand relevant citations that were identified. So there were 2 reviewers that went through these and identified 822 articles, and then 3 reviewers, I believe another reviewer than the initial 2 went through, excluded 582 of those, and so there ended up with about 250 articles that had some teaching versus non-teaching comparison. However, it turns out that out of this 250, only 100 actually had a comparison that could be used in the meta-analysis. So it turned out that for the meta-analysis, there were 100 studies, and the study outcome was mortality. However, mortality was defined differently in terms of time of mortality. So about 60% of the 100 articles, mortality was in hospital. For another 35%, mortality was 30-day mortality, or what that means is that mortality that occurred from discharge up to 30 days, and then a small number of studies looked at mortality beyond 30 days. So even though our outcome is mortality, we have different time frames for when mortality occurred. And then also you note that the span of the studies was quite large, from 1987 to 2008. A real positive, though, is that it had over 20 million patients in the study. So that's quite a few, but the span of the studies isn't is maybe more of a negative, because in terms of mortality, you're going to assume that treatment modalities probably changed maybe even quite a bit over those 20 some years. So the random effects odds ratio was 0.94. And because of the large number of studies, this was statistically significant. However, the I-squared statistic was nearly 99%. So this is saying that the results are primarily due, almost entirely due to differences between the studies. And so in this study, in this meta-analysis, we did a funnel plot, and this is what a funnel plot looks like. So what it does is it plots the log odds ratio with the standard error of the log odds ratio. And so what you want to see in this plot is all of the studies within the 95% confidence intervals, with the smaller studies near the bottom. In other words, the standard error gets larger the smaller the study. The studies near the top are the larger studies. And so what you, as I mentioned, would like to see is that they all fall within the 95% confidence intervals. In this case, you can see that they don't, that there's quite a few of the larger studies that are outside of the 95% confidence interval. So this is indicating that we have some publication bias, or at least in my mind, its bias is also by the timing of mortality, the timing of death in the patients that were included in the studies. So time of death was not taken into account. And then, as I mentioned, virtually all the between study variability was due to differences in the studies. So it would be probably not wise to conclude that there was an important difference between teaching and non-teaching hospitals with respect to mortality because of some of these issues. Okay, and then finally, I want to look at a study that looks at patients with angina but without obstructive coronary artery disease. And so I've just pulled out some of the important parts of this. So the primary outcome was the composite of all-cause mortality and non-fatal MI. So what they calculated to was the incidence or the person time years at risk in order to account for the heterogeneity of follow-up across the different studies. So this is a real plus for their study here, that they're looking at a statistic that is taking into account the follow-up duration. And then they have a paragraph about the confidence intervals and how these are calculated. And so they use the Dersimian and Laird random effects model to estimate summary of the pooled incidence of the outcomes and for sensitivity analyses. And they mentioned that they performed a jackknife sensitivity analysis for the outcomes of interest. So we're just going to look at the primary outcome of all-cause mortality and non-fatal MI. So this is their forest plots. You can see that they have quite a number of studies. And you can see that the effect size, the risk in terms of person years is virtually 1 at the very bottom there, 0.99. So there's the conclusion here is that there's no difference. However, we see that the I-squared is quite high, 96%. So there's quite a bit of variability between studies. And so, we can look at this in, so different ways, and actually they do make some conclusions. But one way that we might look at variability, if you have a really large I-squared statistic, and this is their conclusions, and then they did a meta-regression as well and found 3 different covariates that affected their outcome, even though overall the person years estimate was nearly 1 over 100 person years, not statistically significant. And so this is just illustrates a plot, how they look at the covariates, and with the regression lines drawn in, the smaller the circles, the larger the studies, the bigger the circles, the smaller the studies. And so what I did in looking at the homogeneity issue here was to order the studies from the lowest to the highest effect size. And so what I would like to do is see if I can identify sets of studies where the I-squared is, in this case, I took sort of 10% as a cutoff. They're 10% or less. Other investigators might use a different cutoff, but one that you'll particularly see is 25%, that studies with an I-squared below 25% are considered, more or less homogeneous. And then so what I did is recalculated the pooled effect size and then the confidence intervals. And so if I order from the smallest to the largest, I get this sort of pattern. And so you can see that there are studies where the incident for 100 person years is quite small, whereas at some point it becomes larger than 1, and at the end quite a bit larger than 1. So what I did then is I took the plot here and found groups of studies where the I-squared was less than 10%. And so if you do that, this is what I got. So here's a number of studies there where the estimated effect size was 0.4 with the confidence interval with an I-squared of 0. Then there's a group where it's a little greater than 1, but also the I-squared is 0. And then a third group where the ratio or the incident is greater than 2. However, if you look at the confidence intervals between the 1.1 and the 2.1, you can see that there's quite a bit of overlap. So maybe, we could consider those as one group. And then finally, the last group, which is this last 2 studies, has or 3 studies, has quite a large incident rate of over 5 per 100 person years. And so by doing this, you can identify sets of studies where there's small variability. But then, of course, what you would have to do is you'd have to look at, is there something about these studies that would indicate or that why they're different from another set of studies, or what is it about that set of studies that's identifying the outcome or different outcomes. And so this is the conclusions from the authors of that study. That is actually, again, pretty good. One of the issues being that it's obviously a lot of heterogeneity. They found that obstructive CAD was inconsistently defined, so there's a issue right there. And so maybe that might be one thing we would look at in the studies that that I found that grouped together, maybe how they define obstructive CAD is the difference. Maybe not, but that's a possibility. And then they make some other general conclusions, but in terms of the the study itself, the high heterogeneity is an issue that would need to be examined, and there's different ways of doing that. The one that I like to do is by arranging them in order and then seeing if I can find sets. And then we could go through and see what is different about those sets, if anything at all. So they, as I mentioned, what I would hope is that if there's a demographic or maybe there's a clinical variable that identifies the different groups according to, but grouping them by heterogeneity. So I want to conclude with a summary here of meta-analysis. So this is a tool for combining results of several or many studies. It requires methodological rigor and careful inclusion of homogeneous trials and avoidance of selective exclusion. And there have been a number of instances of meta-analyses where it has become obvious to experts in that area that the studies have been selected to prove a point, or I should say a bias point of the authors. And so we need to also have a common definition of the outcomes, and then to treat the study as a random effect. If the I-squared is 0, then there's no difference between the estimates of random and fixed effects. But typically, you're going to have some I-squared that's not equal to 0, and so that's an issue that will have to be dealt with one way or another, and some perhaps deal with it better than others. So if you are looking at meta-analyses or reading them, published meta-analyses, so as far as evaluating them, as we talked about, you probably first of all want to look at patient populations. And so are the treatment groups the same as far as the patients go? Or do you have a mixture of different patient populations, as we saw in the COURAGE study, or in the meta-analysis that included the COURAGE study? And then, as we mentioned, you want to always treat studies as a random effect. And then heterogeneity is probably the main issue that you'll have to deal with. And as I mentioned, people may have different definitions of what heterogeneity is, as far as defining how high or how low you're going to use as a cutoff to distinguish homogeneity from heterogeneity. And one of the, as I mentioned, one of the cutoffs that you'll typically see is like less than 25% is often considered homogeneous. 25 to to 50%, 50% to 75%. And then if it's 75% or over, almost everybody's going to consider that as high heterogeneity, which means that whatever differences you're seeing between the treatments you're comparing is due to differences in the studies. And then, as I mentioned earlier on, if you want to look at meta-regression to look at whether you can identify different covariates like age or gender, or whatever you might include. But of course, the drawback there is that the studies may not include the same covariates. There may be some overlap, like typically every study has age in it, but some of the other, say, clinical covariates that you might want to look at are not the same across studies. In the past, there hasn't been much assessment of study validity, of the validity of the individual studies, but in more recent times, this has been included in meta-analyses. In fact, it might be a requirement of some journals. But anyway, study validity can be assessed in different ways. There are some articles that come up with a numerical score for study validity and try to include that in the calculations of the effect size, the overall effect size, as well as heterogeneity. There's others that just, and there's checklists that you can find on the internet that you can include that determines how good the study is. Like, so obviously one of them is going to be randomized trials, will be at the top of anybody's list as far as a good study. Data collection, but I say these are sort of mostly just a checklist, but you see those in many analyses now. So the one, I guess, my takeaway from this is when you read meta-analyses, be very skeptical because there's a lot of potential for biased results or biased conclusions. And so when you look at a meta-analysis and evaluate it, you want to take into account these things that we've talked about and start out by being skeptical of it. So I might just add that if you want to do meta-analyses yourself, there's actually quite a bit of software online, and I think quite a few are free software for doing meta-analyses if you want to engage in meta-analyses yourself. So I have some of the references for meta-analyses. The first two are the ones that studies that I went over, and then the last two are a couple of more statistically oriented articles of doing meta-analysis. So with that, I will conclude, and we'll want to mention that this is the last statistical seminar until next fall. So we will be off June, July, and August, and then come back in the fall to resume the series. So I want to thank you for your time. And if you have any questions or any issues that you want to discuss, you can email me at my MedStar address there. And then also, I will say that the slides and the presentation will be made available to those who have registered for the seminar. So I will, at this point, then wish you a good summer, and then hope to see you back again in the fall. Thank you for your time.